Welcome to your OMG video on work done and energy. So we'll be looking at work done, kinetic energy and gravitational energy, and at the end we'll be looking at Hooke's law. So work done is on an object or by an object is when it is moved against a force. So it's got to move a distance against a force. Okay, it is equal to the energy transferred by or to the object. Okay, we calculate that using work done equals force times distance, and that's the distance moved against the force. Okay, work done is measured in joules because it's equal to the energy transferred. The force is measured in newtons, and the distance is measured in meters. It will be important to make sure you transfer or change to meters if you have other units like centimeters or kilometers. Okay, so for work to be done, as we said, there's got to be a force and there's got to be a distance moved. Okay. If the object is not moved against the force, there's no work done. Okay, so we've got some examples here. So work is done if you lift weights from the ground to above your head. Okay, lifting jars from a bag and putting them up on a shelf. Okay, it's important they move up. They've changed their height. Okay, opening a door, you're pulling against the door, you're providing a force and moving the door. Okay, so carrying weights across a room at the same height. Okay, you've not moved against a force. Okay, you've not lifted the weights up. Therefore, there's no work done. Okay. A shelf holding up jars, the jars are staying still, there's no work done. Okay, if you hold a door open, again, there's no work done, you're not moving a distance. Okay, an example of work done. So we've just gone for a weightlifter lifting weights. Okay, he lifts, or they lift 100 kilograms from the ground to above the head. What is the work done? So first up, you write your equation. Okay, we're going to have to underline the important information. Okay, so we've got 100 kilograms and 2 meters. We substitute into the equation, and we get 100 times 10. Okay, that's because we need to work out the force. Okay, so the force, if you remember, we got weight equals mass times gravity. Okay, which equals 100 times 10 on Earth. Okay, and then we multiply that by 2 because that's the distance you've moved. Okay, and that just gives us the amount of work done. Okay, so kinetic energy. Any moving object has kinetic energy. It's movement energy, okay? We've got 2 equations for that. Okay, so kinetic energy equals the mass times the velocity squared divided by 2, or I always remember it as kinetic energy equals half mv squared, okay? It gets a little bit complicated when we have to rearrange. If you're given the energy and the mass and you need to find the velocity, we obviously need to square root those things, okay? You'll be able to do that by rearranging, obviously. And then taking the square root, okay, which I'm sure you'll be able to do using your maths knowledge and your numeracy skills. Okay, so kinetic energy, again, is an energy, so it's measured in joules. Mass, we know, is measured in kilograms, and velocity, we know, is measured in meters per second, okay? Remember, you've got to square the velocity, okay? It's not just velocity, it's velocity squared times the mass divided by 2. So it's important that you get that right on your calculations. That's why we want to work through step by step. Okay? So an example would be a runner of mass 50 kilograms moving at 2 meters a second. What is their kinetic energy? Okay, so we're going to write out our equation. Kinetic energy equals half mass times velocity squared. Okay, let's underline our important information. We substitute that in. Okay, so we get half times 50 times 2 squared, and you can see that I've done half times 50 first to give 25, and then the 2 squared to give 4, and then that just gives us an energy of 100 joules. Okay? Right, so gravitational potential energy. If an object increases its height, it gains kinetic gravitational potential energy. If it decreases its height, it loses gravitational potential energy. Okay, so the change in gravitational potential energy is equal to the mass times the gravitational field strength times the change in height. Okay, so GPE equals mg delta H. Yeah, so mgh basically. Mass in kilograms again, gravitational field strength newtons per kilogram, and height in meters. Okay, gravitational potential energy is an energy, so it's measured in joules. So again, an example. We've written our equation. So GPE equals mgh, okay, and then we can underline our important information. Yeah, we've got the mass, the change in height, okay, and over here we've got a gravitational field strength, okay. You should know that gravitational field strength on Earth is 10 newtons per kilogram, okay? We then simply just substitute those numbers in, yeah, so we get 60 times 10, yeah, so 60 is the mass, 10 is the gravitational field strength, multiplied by 1,200 meters, okay, and that gives us our energy there, okay? So just some simple multiplication times in. Right. The law of conservation of energy, okay, is really important here, okay? So the energy cannot be made or destroyed, only transferred from one form to another. So the total energy in a system must remain the same at all times. That's from the start to the end, okay? So an object is falling, its gravitational potential energy at the start will be equal to the kinetic energy when the object is falling, okay? Or when it's about to hit the ground, I suppose. So if I draw a roller coaster, okay, there's our height h, excuse the diagram, that's got a mass m, okay, so it's got a GPE up here, okay, when it gets to the bottom, obviously GP is gravitational potential energy, still got the same mass, okay, you can see that there it is at the bottom, okay, and it's going to have a kinetic energy at the bottom, okay, so GPE is transferred to kinetic energy, okay, so gravitational potential energy at the start equals the kinetic energy at the end, okay? All right, and if you're ever asked, you can then put the two equations equal to each other. So we get mgh equals a half mv squared, okay? So in that way we can find out the velocity, if we're told the gravitational potential energy. If we're told the velocity at the bottom, we can, and the mass, well, we don't actually need the mass, we can work out the change in height that's taken place by rearranging, okay? You do that in exactly the same way as you do your usual calculations, substitute in the numbers that you know, okay, and then rearrange and make whatever you're looking for the subject, okay? So, Hooke's law, okay, Robert Hooke discovered that the amount a spring stretches is directly proportional to the force applied to it, okay? It's important that you recognise that we're talking about how much it stretches by, and I'll show you a diagram of that in a second. So we've got force equals the spring constant times the extension, okay? Each type of spring will have its own spring constant. It will be different. And here it says extension equals the stretch length minus the original length, okay? And I'll show you that in a second. This is true up to the elastic limit. We'll have a directly proportional graph, yeah? So as the force increases, the extension will increase at a steady rate. When the elastic limit is reached, that's when the spring stops returning to its original length when the force is removed, okay? So we've all seen it. You can stretch a spring. If you pull it too far, okay, it then doesn't go back to its original shape, okay, and its original length. Okay, this is true for other materials, stretching materials as well. At this point, the spring changed from behaving as an elastic material to behaving as a plastic or inelastic material, okay? So when we talk about plastic material, think about the plastic bags, the cheaper bags for life, okay? If you put too much shopping in those, the handle stretches, okay, and it won't return back to its original shape, okay, because it is a plastic, it's not elastic, okay, whereas an elastic band will return to its original shape and size. Okay, so this is what we're talking about for the length, okay? So what I'm going to do is, here is my original length, okay, L for my spring. Okay, now I'm going to draw a line across this. Okay, so a horizontal line. Okay, the extension, therefore, for this one at the end here, that is my extension x. Okay, so for this one, that's the extension. Okay, so it's the length, yeah, of the spring, take away the original length. Okay, and that's what we mean by extension. It's really important that that is what you plot on your graph if you're ever asked to plot a graph of that. Okay, so please answer your OMG questions with this video. Obviously, you can watch the video again and pause it as and when you need. Right, thank you very much.